If the student volunteers can please start the recording. Thank you.
My name is Dan, and today I would like to talk to you about semantic cut elimination for the logic of bunch applications. Let me start briefly by explaining the title and the main topic of this work. The logic of bunch applications, or BI for short, is a non-classical logic used for reasoning about separation and determinateness of resources. In particular, it forms the propositional basis for separation logic, which we have seen during some of the talks yesterday. Cut elimination refers to a standard result in the proof theory of logics. We will see the precise statement later, but essentially cut elimination implies that for every formula phi, if phi is provable at all, then there exists a proof of phi which only mentions subformulas of phi. That is, only formulas that already occur in phi itself. The proofs of cut elimination for various logics that you see in the literature are usually very involved and contain a lot of details and case analysis. In this work, I propose a semantic approach to proving cut elimination for BI, by which I mean a proof that goes through some semantical model. I believe that this kind of proof is more amendable to formalization and more extensible. To support this claim, there is a co-formalization of this proof, including some extensions, available online. In the remainder of this talk, I would like to explain the problem in more detail and sketch the proof. I will conclude the talk with some reflections on the formalization process. Let's first talk about the logic of bunch applications. BI is a logic that you obtain by freely combining intuitionistic logic and multiplicative linear logic. It has the usual connectives like disjunction, conjunction, and so on, but it also includes linear connective, empty, star, and the magic wand. Intuitively, propositions in BI denote ownership of resources. For example, phi star psi holds for disjoint resources or separate resources, and the empty proposition states that there are no resources available. Like many logics, BI comes with a proof theory in a form of sequent calculus. Sequent calculus is a logical system in which one reasons about judgments of the form context, proofs, formula. So you have a formula on the right-hand side of the turnstile, and you have a context, which in the case of intuitionistic logic is a list or multiset of formulas. We think of a context as a list of hypotheses or assumptions. For each connective, there are two corresponding rules. A rule which tells you what to do if you have a connective on the left-hand side of the turnstile, and a rule which tells you what to do if you have a connective on the right-hand side of the turnstile. Here you can see the left and the right rules for the intuitionistic conjunction. The left rule says that if we have phi and psi as an assumption, then we can split it into two assumptions, phi and psi. The right rule says that if you want to prove phi and psi, then we need to have separate a proof of phi and a proof of psi. We also have structural rules. In intuitionistic logic, we have contraction and weakening. Contraction states that we can duplicate whatever assumptions that we have in the context, and the weakening states that we can throw away any assumptions that we don't need or we don't want to. In the sequent calculus for BI, the two connectives conjunction and star are externalized as two different operations on the context. Whenever we see conjunction, we connect the two resulting formulas using a semicolon, and whenever we see star, we connect the formulas using a comma. Crucially, only the semicolon admits the rules of weakening and contraction. This corresponds to the idea that conjunction behaves intuitionistically, while star behaves linearly. So, because we have two types of connectives on the contexts are no longer lists or multiset of formulas. Instead, the contexts have this tree-like shape and are called bunches. So the nodes in this tree are labeled either with a comma or a semicolon, and the leaves are formulas. Because of this nested structure of context, the left rules and the structural rules, they all can be applied deep inside a bunch on some particular substrate. Finally, the last rule of the sequent calculus to mention is the cut rule. it says that if we can prove some formula psi, then we can essentially use psi as our assumption. And intuitively, the cut rule allows us to prove and use intermediate lemmas. Alternatively, you can think of the cut rule as a rule that forces the probability relation to be transitive. An important metatheoretical result about sequent calculus is the cut elimination theorem. It states that everything that is provable is also provable without the cut rule. That is, if we have a proof of some formula phi, then we also have a proof of phi in the sequent calculus without the cut rule. And here on, we're going to use this notation, Gentzen-style with a subscript, to denote cut-free probability. Cut elimination is important because it implies the subformula property. If there is a proof of phi implies psi, then there is a proof of it that only involves formula that are already present in phi and psi. As such, cut elimination is an important ingredient in the proof search toolbox. The usual way of proving cut elimination is syntactic or direct. It basically proceeds as following. Given a proof derivation, we look at the first instance of the cut rule that we can find, and basically we do a case analysis by looking at which derivations were used in this rule. Then we use this information to either simplify the proof or to shuffle the proof around, and in any case what we do is we replace a particular instance of the cut rule with a number of smaller cuts for some notion of smaller. In my view, this kind of direct proofs have some limitations. Firstly, there are simply a lot of cases and details to consider. Secondly, you need to come up with the correct order in cuts. You need to define what it means for one cut to be smaller than the other, and to show that this is in fact a well-founded relation. Doing this can sometimes be tricky, especially in presence of explicit structural rules. Also, and this is specific to the case of BI, we have this tree-like shape of bunches of context, and the fact that rules can be applied deep nested inside the bunches. All of this significantly contributes to the complexity. Because of these factors, non-formalized proofs of cut elimination found in literature can be quite fragile and known to be error-prone. In fact, for some of the logics, formalized proofs of cut eliminations uncovered a number of errors or mistakes in the original pen and paper proofs. Nonetheless, formalizing this kind of proofs directly can be quite tough. The sheer number of cases and syntactic complexities makes it tedious and laborious. And complicating terminating measures and additional friction, at least in the proof assistants like Coq, which are more geared towards things like structural induction and structural recursion. Instead of formalizing a syntactic proof, I would like to argue for what I believe to a more tractable proof of cut elimination, a semantic proof. By a semantic proof, I mean a proof that goes through some model C, which has a particular nice property. The property that we want is that if a formula phi holds in the model C, then phi is provable without using the cut rule. As a side note, as models, we'll consider algebraic models, so BI algebras. The details of what is a BI algebra is not important, but essentially it's a set with a pre-order and all sorts of functions and operations that allow us to interpret BI connectives. What you need to know is that BI algebras are sound with regard to the sequent calculus, meaning that if phi proves psi is derivable, then the interpretation of phi is going to be below the interpretation of psi. So the way I'd like to think about it is to take inspiration from the proof of completeness. A typical algebraic completeness proof goes through what is called a Lindenbaum-Tarski algebra, which is defined in the following way. For each formula phi, we associate an equivalence class of formulas that are interprovable with phi. We then say that the equivalence class of phi is below the equivalence class of psi if phi proves psi. This turns out to be a well-defined partial order. Then the collection of all equivalence classes with this order forms a BI algebra. An important property of this algebra is that the interpretation of a formula phi is the same thing as the equivalence class of phi. Now, this model allows us to prove completeness. If phi implies psi holds in all the models, then in particular, the interpretation of phi is going to be below the interpretation of psi in this model L. This in turn means that phi proves psi, and this concludes the completeness proof. As you can see, the real work here is to show that L is indeed a model and that it has this particular property about its interpretation. So as a starting point for cut elimination, we can consider just using cut-free probability instead of regular probability in the definition of L. However, we will run into the following problem. We need to show that the ordering of the equivalence classes is intransitive in order for it to be a partial order. However, showing this is essentially showing the transitivity of the cut-free probability relation, which amounts to the same thing as showing cut elimination. So we are back to square one. In order to mitigate this, instead of using equivalence classes, we are going to consider sets of predecessors in the following sense. For each formula phi, we are going to associate the principal set of phi, which is the set of contexts from which you can prove phi without the cut rule. Then we are going to consider set inclusion, which is automatically a transitive relation. Subset inclusion is a good candidate for the following reason. First, note that every formula is included in its own principal set. That is because for any phi, phi proves itself without the cut rule. Then, if a principal set of phi is included in the principal set of psi, we can safely conclude that phi proves psi without using the cut rule. However, the collection of principal set with a subset ordering is not going to form a BI algebra. In particular, we cannot use the sets theoretical operations such as that union and intersection of sets because principal sets are not going to be closed under those operations. We resolve this issue by forcibly closing the principal sets under arbitrary intersections. That is, the elements of the algebra that we're going to consider are going to be sets of this form, where I is an arbitrary indexing set and phi I is a formula. Now, there is actually an abstract mumbo-jumbo reason for why this works and why this forms a BI algebra, but essentially it boils down to this. So we have this closure function. It takes an arbitrary set X of bunches and returns the smallest set in C, which contains the set X. It turns out that this function allows us to transfer a lot of the operations from the power set algebra to the algebra C. For example, the disjunction in C corresponds to the closure of the union of two sets. And the star operation can also be written in terms of the closure operation and some monoidal product on the power set algebra. Finally, this model satisfies the property that we want. If the interpretation of phi is included in the interpretation of psi, then phi proves psi without the cut rule. Then, if a sequent phi proves psi is derivable, we know that the interpretation of phi is going to be included in the interpretation of psi, which will give us a cut-free proof rule of the same sequent. To sum up, this gives us a semantic-based proof of cut elimination by going through this algebra C. I believe that this approach is more modular and more amendable to formalization, at least in proof-as instance like Coq. In the paper you can read more details about the proof and also about two extensions that we consider. Extensions of BI with some classes of structural rules and extensions of BI with a box modality, which is an S4-like modality added to BI. Now, before I finish, I would like to say a couple of words about the formalization. The basic formalization, without the extensions, is around 650 lines of specs and 2,500 lines of proofs. I tried a number of different representations for the elements of the algebra C, and I found the extensional representation the easiest to work with. By extensional representation, I mean that the elements of C are essentially predicates or bunches, or sets of bunches, that satisfy some particular closure property, which is a proposition. This is opposed to a more intentional representation, which would code elements of C explicitly. In order to reason with this representation, it's good to have propositional extensionality. For this, I use setoids and setoid rewriting. Setoids are actually used in lots and lots of places in the formalization, And the standard library that I use, stdpp, it has a number of type classes that integrates it very well with the whole setoid business. So overall, I have to say that I had a very positive experience with this sort of stuff. And finally, there were still places in the proof where you would have to reason about some syntactic things. For example, it is very common to have equations of this form where you can decompose a bunch delta into a sub-bunch gamma and some context delta prime. I find it useful to make inductive characterizations of such equations as inductive predicates in Coq. That is, you write down an inductive system that would generate all the equations of this form. Then you can use the normal Coq induction principle to reason about these equations, which turns out to be very nice. You can see more details of this in the paper. Thank you very much for listening, and let me know if you have any questions.
Thank you very much. So we already have 2 online questions. Let's start with an online question. If we can post the question from Neil, please. Okay. Does the proof go through using purely constructive features? In other words, does your proof also give an algorithm for computing cut-free normal forms?
Can you hear me?
Yes, we can.
Yeah, thanks. That's a good question. It's the proof is purely constructive. I did, however, not manage to actually execute it and run it inside Coq. There were some problems with deciding which things to make opaque in order for it not to blow up. But well, the bottom line, I did manage to actually extract an algorithm for that. Another reason is that I use a prop, an impredicative prop, a lot, which gets erased. So I couldn't also extract it directly to a camel. I think it would definitely be very interesting to see how we can extend it to get an actual algorithm. But then I think it would actually require some new theory that would, we would have to go to something that's more close to normalization by evaluation or something like this that works explicitly with terms and tracks them.
All right. Thank you. Let's now see if we have a local question in Philly.
Any questions here? I think Leonard had the same question that was just asked.
All right. So we have a couple of more online questions. If we can show the question by Dominic, please, by Dominic Kirst. Would the completed algebra be complete enough to interpret first-order BI if this exists? And would this still allow for semantic cut elimination?
Yeah, that's a good point. So actually, the algebra is complete in the sense that it's a complete poset. So you can interpret quantifiers there. I just haven't done that because I didn't want to formalize binders in first-order logic.
So a cylindric BI algebras or the like, probably. You would need cylindrical, periodic. All right. So okay, there are quite a few questions, online questions. Let's take another one. The question by Daniel. Please, can we post this question by? In the conclusion of the paper, you mentioned an interest in generalizing this to type theories and recovering the categorical normalization by evaluation approach. Does the reverse hold? Does what you have done here somehow specializes or adapts the gluing proofs for MLTTs?
Yeah, so I don't think the reverse holds in the sense that, well, at least the way I think about it, the way that I think about, NB for type theory or something like this, you usually have some kind of category of pre-sheaves, and then you go to sheaves, and then that gives you the model from which you're going to extract your property. And the construction here doesn't really fit into this framework. So I guess, yeah, the algebra of sets can be, I mean, you can think of it as, okay, we can generalize it to pre-sheaves, but then this next step of having this closure operator, it doesn't really seem to correspond to the kind of sheaf conditions that you see in B. So the bottom line is, yeah, I would like to know more about the connection between this and B, but haven't managed to get really further there.
All right. So we have another one from Maven. If we can pose this, he asks, is there any topological intuition to be had about your algebraic structure?
Yeah, I don't know. I'm not sure. So I mean, so the closure operator, it's kind of satisfies some condition. Well, it behaves a bit like the closure operator in in point set topology. But I don't know if that's actually. I mean, so there's a lot of sort of intuition from that, but it's not like, I don't know if there's a good, let's say, geometrical way of thinking about it.
Okay, let's try a local question if we have any. If not,
and I don't think there are any.
Okay, we have another online question from Benjamin Werner. If we can, he says, "Great stuff. I realize the question seems stupid, but I wonder whether it would be imaginable to do a semantic strong normalization proof, like associating the set of terms normalizing to the normal form."
Yeah, I mean, I think it should be possible, because we know how to do strong normalization proofs for, let's say, natural deductions presented as lambda calculus, for example. So it should be possible, but yeah, I don't know quite exactly what is the step to go there.
All right. I also have a question, actually. So the short version of the question is, where is the magic? And the longer version is, if you take your two proofs, so I guess a way to translate this is, where's the syntactic proof, the really neat syntactic proof hiding in there? So if you take your proof that basically deduction implies inequality in all the BI algebras, and then the proof that specially constructed BI algebra proves shows cut-free deduction, and you compose this, there is this, it sounds superficially, it sounds like there is a syntactic proof, an elegant syntactic proof that hides in there, inspired by your semantic approach.
Yeah, I mean, absolutely. So I mean, there's no, there's nothing for free, right? You still have to do some work, some syntactic work. But so the idea is that, so all these conditions is all the syntactic stuff is pushed to the conditions that you need to show that this is indeed the model. And essentially, I don't remember off the top of my head. I think there's some discussion about it in the paper, but you need to show that certain rules are invertible, like the left rules for certain connectives, and that you have that the right rule for implication and for the magic wand is also invertible. Okay. So I think those are the main syntactic ingredients that you need to show.
Okay, so you see the syntactic proof that follows in there. You have it visualized, so to speak. Yeah.
Yeah, not completely, but there are definitely details that, okay, this is explicitly what we need to prove. Let's say if we want to adapt this to a new logic, then this is what needs to be shown of the calculus itself.
All right. Thank you very much. So let's
Thanks.
end down again.